Welcome. This question says, this circuit consists of a 6-volt battery, so let's put that in, a 3 farad capacitor, let's put that in, and a 4 ohm resistor, let's put that in. So I'll squeeze in my units. 6 volts, okay. And what is the potential difference across the capacitor immediately after the switch is closed? Okay, boom, boom, boom. So I've closed my switch, and now my potential difference is applied across both components. Maybe they'll divide the potential difference. The capacitor, the potential difference across the resistor is given by V is equal to IR. So it has a potential difference which is equal to the current flowing through it times the resistance of it, and the potential difference across the capacitor equals Q over C. So its potential difference equals the charge over the capacitance value. And I know that my EMF, that's that curly E, must equal the voltage across my capacitor plus the voltage across my resistor. So there's my background. And I can see that immediately after I close the switch, I've not had time to have any charge added to the capacitor. So the voltage across the capacitor equals 0. And I can see that the two potential differences have to add up to 6. If I have a total of 6 and VC equals 0 because there's no charge on the capacitor, that means that all of the 6 volts must be across the resistor. So I can say, oh, my voltage across the capacitor equals 0 volts because there's no charge. And I know that the voltage across the resistor must be 6 volts because the potential difference has to be dropped across, the combination of these two. So my answer is the voltage across the capacitor equals 0 volts immediately after the switch is closed. Then my next question is, what is the time constant of the circuit? And the time constant is a figure of merit, and it equals the resistance value times the capacitance value. And this equals, well, in this case, it's going to be my resistance value, which is 4, times my capacitance value, which is 3, both in standard units, of course. And that gives me 12, and it's a time constant, and the standard unit for time is seconds. So the time constant for this circuit is 12 seconds. What does that mean? That gives you an indication, if we look at, say, charge versus time, that gives you an indication of how quickly a RC combination will charge up, or how quickly it will discharge. It's a figure of merit. It tells you how long it takes to get to about 63% of the full charge. Next question, how long will it take for the capacitor to get to 63.2% of the charge? Time to 63.2% of full charge equals tau, which equals 12 seconds. So that's a good figure of merit. It's a really useful thing. You get a feel for how sluggish the combination is in charging or discharging. And then what is the potential difference across the capacitor? Not 12 seconds, but 20 minutes after switch S is closed. Well, if I look at this impromptu diagram here, 20 minutes, I'm way down here. And I've reached that constant, fully charged condition. And so when I'm fully charged, if I look back and say, well, remember V equals IR, and V is equal to Q over C. So after 20 minutes, I am fully charged. And after 20 minutes, there's no current flowing in my circuit because there's nowhere for the current to go. If I'm fully charged, I'm fully charged. I'm no longer charging up the capacitor. I've charged it. And so my current is 0, so my voltage across the resistor is 0. My charge is fully, my capacitor is fully charged, so all of the EMF is dropped across the capacitor. So I can say that the, remember that my EMF is equal to the voltage across the capacitor plus the voltage across the resistor. If the voltage across the resistor is 0 because there's no current flowing, then all of the voltage must be across the capacitor. What potential difference is across the capacitor after 20 minutes? VC is as much as we can have. And if there's a 6 volt EMF, then all 6 volts is across the capacitor. And then the last little bit, what is the potential difference across the capacitor 4 seconds after the switch is closed? Well, my charge on the capacitor, I can say my charge on the capacitor is equal to my capacitance times my EMF, my electromotive force. And for charging, it's 1 minus E to the minus T over tau, and tau is RC. So I've got to do some calculations here. Let's write my numbers in. So this would be my EMF is 6 times my, my capacitance. Let's do them in the right order. So my capacitance is, is 3. My EMF is 6. And then I have 1 minus E to the minus 14 over my RC. My RC is 12. So that equals, let me get my calculator out. And with these things, I'm going to do the exponent first. So it's E to the minus 14 divided by 12. That gives me a fractional number. It's 1 minus that fractional number, and then I multiply that by my number of farads, and I multiply that by my EMF. And so I'm getting 12.39. So this is, where's my pen gone? So this is, here we go, 12.39, and that would be coulombs. So now I'm in trouble squeezing this in, but I can see from here my VC is equal to Q over C, which equals 12.39 over my capacitance. My capacitance is 3, so that's going to equal 4.13 volts. And let's have a look. At the time constant, I should be 63% charged, which means I should have 63% of the potential difference. So I'm a little bit, 63% would be a little bit over 4, and I'm a little bit over 4. So it looks like a decent answer to me. So there's the typical layout of these kind of questions. There's a bit of conceptual stuff about what's the potential difference immediately after you close the switch to charge up the capacitor. There's some knowledge about what the time constant is and how you find it. And then there's a little bit of conceptual about what happens once the thing is fully charged. And then there's usually some kind of calculation about what happens during the transient while you're going from 0 charge to fully charged. And I can ask you about charges, I can ask you about potential differences, etc. And I can also discharge. So so there's the pattern of questions in this section.